All right, so buckle up, everybody, because today we are diving deep, like deep, deep.
Into the mind of one of the most brilliant physicists.
Yeah, ever.
Yeah.
We are talking Stephen Hawking.
Oh, yeah.
His books, especially A Brief History of Time, those are like the ultimate guides to the universe.
It's true. And you know, the amazing thing is you don't need a PhD to get it.
Exactly. He explains like black holes and the Big Bang, all this crazy stuff. But somehow it makes sense.
He really had a knack for taking like mind-bending physics and making it a story.
Totally. So today, we're going to try and do the same thing, break down some of the big questions Hawking tackled.
Like, how did the universe begin?
Where is it going?
Is time travel even possible?
Ooh, and is there like a grand design to it all? We're going to get into all that and more.
What I find fascinating is how Hawking takes us on this journey, you know, starting way back with ancient thinkers.
Oh yeah, like way before telescopes and all that.
Exactly. People were already trying to figure out the cosmos just by looking up.
So who are some of these cosmic pioneers? Like, give us some names.
Well, got to start with Aristotle, like way back in 340 BC.
Aristotle. Okay. Now, what did he figure out?
He actually deduced that the Earth was a sphere.
Wait, seriously? No satellites, no nothing, just pure brain power.
Just observation. He looked at lunar eclipses, right? The Earth's shadow on the moon.
Right.
It's always round. Also noticed how ships, when they sail towards you, you see the sails first, then the...
That's true. It's like coming over the horizon.
Exactly. Only makes sense on a curved surface.
That's some impressive reasoning. Got to give him props.
Oh, for sure.
But so, Aristotle got the Earth's shape right, but what about the whole universe? Did he think we were the center of it all?
He did, yeah. That was the prevailing view for a long time. Very human-centric.
Makes sense, right? We're down here, everything seems to revolve around us.
Right. But then along comes Copernicus, and boom, shifts everything to the sun being at the center.
The Copernican revolution.
All right, so we're moving in the right direction, at least in our solar system. But did they have any clue back then about galaxies, like beyond our own? Not really, no. That whole concept of billions of galaxies out there, that was still way beyond their understanding.
It's crazy how much our perspective has changed, right? From thinking we're the center of everything to being this tiny speck in a vast universe.
It is, and this evolution of ideas, it's key to what makes Hawking's work so compelling.
Totally. Okay, so Copernicus puts the sun in its rightful place, but then what happens next?
That's where the big man comes in, Isaac Newton.
Newton. Gravity, right.
Yep, his law of gravity, it changed the game completely. Explained how objects attract each other.
And it worked? Like predicting the movements of planets?
Exactly. Powerful stuff. But even Newton, he had his mysteries.
Okay, I'm intrigued. What stumped the great Newton?
Well, one of the big ones was action at a distance.
Action at a distance. Okay, break that down for me.
Like, how can gravity act instantly across huge distances? He even called it spooky. Like, how does the Earth know to be pulled towards the sun?
Yeah, that is weird when you think about it. It's like invisible strings pulling everything together.
Right. And these questions about gravity, about the nature of time, they paved the way for, well, you guessed it, Einstein.
Einstein. Okay, he's like the ultimate physics rock star.
For good reason.
Yeah.
His theories, special relativity, general relativity, completely changed how we see the universe.
So Einstein, how did he shake things up?
He said, time is not absolute. It's relative to your motion.
Wait, so the faster you move, the slower time goes for you?
Exactly. It's mind-bending, I know. He introduced this idea of space-time.
Space-time. Okay, now we're getting to the deep stuff.
Yeah, it's like the fabric of the universe, space and time woven together. And gravity, it's not a force, it's a curvature in this fabric.
Whoa, okay, so massive objects like stars, planets, they're actually warping space-time.
Precisely. And that warping, it causes gravity. Like a bowling ball on a trampoline creates a dip, things roll towards it.
Okay, I kind of see it. And this warping, it also affects time, right?
Yeah.
The stronger the gravity, the slower time goes.
Exactly. That's why near a black hole, time would slow down for you compared to someone on Earth.
So black holes are like time machines.
Well, not exactly time machines, but they do mess with time in extreme ways. We'll get into that more later.
Okay, I'm on the edge of my seat here. But before we jump into black holes, let's rewind a bit. While Einstein's doing his thing, what else is going on in astronomy?
Right around the same time, there's this astronomer, Edwin Hubble, making a groundbreaking discovery.
Okay, Hubble, what did he find?
He was observing distant galaxies, and he noticed their light was shifted towards the red end of the spectrum. It's called redshift.
Redshift, okay. And that means?
It means those galaxies are moving away from us. And it's not just a few, it's all of them. Like the whole universe is expanding.
Wait, the whole universe. Everything's moving apart.
Yeah, and if you rewind that expansion, it implies that everything was once incredibly close together, incredibly hot and dense. That's the essence of the Big
So
Bang.
the Big Bang was like the starting point.
It's the best model we have, yeah. It explains the expansion, the background radiation we see in space.
So if there was this Big Bang, does that mean the universe has a center? Like a place where it all started?
Ah, good question. But actually, no. The Big Bang wasn't an explosion in a specific spot. It was the expansion of space itself, everywhere at once.
Whoa. Okay, so there's no center to the universe.
Nope. It's like, imagine the surface of a balloon as it's being inflated. Every point is moving away from every other point.
Okay, I'm picturing that. So the universe is expanding, but what started the expansion? And what was there like before the Big Bang?
Those are the million-dollar questions. And even Stephen Hawking, he didn't have all the answers. But by exploring his work, we can get a glimpse of how he tackled these mysteries.
I'm ready for some mind-blowing insights. Let's keep going. Okay, so much to unpack here. But I gotta say, those black holes, they really capture the imagination.
They do, don't they? They're like the ultimate cosmic mystery.
Totally. Just the name, black hole, it sounds so ominous, like these all-consuming voids in space.
They definitely have a certain mystique. But, there's more to black holes than just being cosmic vacuum cleaners.
Okay, I'm listening. So what exactly is a black hole? Like, how do they even form?
Well, a black hole is basically a region of space-time where gravity is so intense that nothing, not even light, can escape.
Nothing. Not even light. That's intense.
Yeah, we're talking extreme gravity here.
Yeah.
They form when massive stars, like much bigger than our sun, collapse at the end of their lives.
So all that matter in the star just gets squeezed into a tiny space.
Exactly. Imagine, like, the Earth compressed into something the size of a marble. That's the kind of density.
No wonder nothing can escape. But what would happen if you got too close to a black hole? Would you just get sucked in, like, instantly?
It's not exactly like getting sucked into a vacuum cleaner. It's more about crossing this point of no return called the event horizon.
Event horizon. Okay, so once you cross that, there's no going back.
Nope. And here's where things get really strange. Hawking described how near a black hole, time itself gets warped.
Time gets warped, so like time travel.
In a way, yeah. As you approach the event horizon, time slows down for you compared to someone farther away.
Okay, I'm trying to picture this. So like if I'm falling into a black hole and you're watching from a safe distance.
Right. From your perspective, it would look like I'm moving slower and slower, and the light coming from me would get redder and redder, eventually fading from view.
So it's like I'm frozen in time at the edge of the black hole.
Pretty much. But for me, the one falling in, I wouldn't necessarily notice anything special as I crossed the event horizon. But then the intense gravity would start to, well, stretch me out.
Stretch you out. Wait,
Oh.
why?
Yeah, it's called spaghettification, not the most pleasant image.
Spaghettification. Okay, that sounds kind of terrifying.
Basically, the gravity pulling on your feet would be way stronger than on your head. You'd get stretched like, well, spaghetti noodles.
Let's not dwell on that image too long. But okay, so that's what happens to someone falling in. But what about all the stuff that black holes, swallow up? Does it just get crushed into oblivion?
For a long time, scientists thought so, yeah. Like, whatever falls in is gone forever. But Hawking's research showed that black holes, they aren't completely black after all.
Wait, what? I thought the whole point is that light can't escape, so how can they not be black?
That's where quantum mechanics comes in, and things get even weirder. Hawking discovered that black holes actually emit radiation, very faintly, due to quantum effects near the event horizon.
Black holes emit radiation. But how?
It's complicated, but basically these pairs of virtual particles, they pop in and out of existence near the event horizon. Sometimes one particle falls in, the other escapes, carrying away a tiny bit of energy.
So black holes are slowly leaking energy. Does that mean they, eventually disappear?
Yep. Over incredibly long periods, black holes can actually evaporate completely. But we're talking timescales way longer than the current age of the universe, like ridiculously long.
Okay, so for now, black holes are still the cosmic champs. But this idea that they evaporate, it raises another question, right? What happens to all the stuff that fell in?
Exactly. Does the information just disappear? That's the black hole information paradox. Physicists are still debating it.
It's like information can't just vanish,
Okay.
right? There's got to be some explanation.
Yeah. There are different theories out there, some pretty wild ones. Some say the information is encoded on the event horizon. Others talk about, like, new dimensions and stuff.
It's amazing how we went from ancient Greeks figuring out the Earth's shape to black holes and quantum mechanics.
It's a wild ride, that's for sure. And we've only scratched the surface of what Hawking explored. We still need to talk about quantum mechanics itself.
Bring in the quantum weirdness. I'm ready. Okay, so we've traveled from ancient ideas about the cosmos all the way to black holes evaporating over, like, billions of years.
It's been quite a journey.
Yeah, but I'm feeling like there's more to explore.
Oh, there's always more. Now, we've been talking about the universe on a grand scale, right? Stars, galaxies, all that.
Right, the big stuff.
But to really grasp how it all ticks, we need to zoom in to the opposite end of the spectrum.
Okay, so instead of going bigger, we're going smaller.
Way smaller. To the realm of the very small, the subatomic world. That's where quantum mechanics rolls.
Quantum mechanics, all right. I know it's, like, super important, but also kind of mind-boggling.
It's where things get really weird. Even stranger than black holes, some might say.
Stranger than black holes. Okay, now you've got to explain this.
Well, in the quantum world, the rules of classical physics, the ones we're used to, they just don't apply.
So, like, Newton's laws and all that, out the window.
Pretty much. Down there, particles can act like waves, and waves can act like particles. It's all fuzzy and probabilistic.
Fuzzy and probabilistic. Okay, my brain's already hurting. What does that even mean?
It means instead of saying this electron is here, we talk about the probability of finding it in a certain region.
So it's not in a specific place. It's, like, spread out.
In a way, yeah. It's like it exists as a cloud of possibilities until we measure it. And the act of measuring, it actually affects the electron.
Whoa, hold on. So we're changing reality just by observing it.
That's the crazy thing about quantum mechanics. The observer is part of the experiment.
Okay, that is mind-blowing. Are there any, like, experiments that show this weirdness in action?
Oh, yeah, tons. One of the classics is the double slit experiment. It shows this wave-particle duality thing.
Okay, so walk me through this double slit thing.
Imagine you shine a beam of electrons at a barrier with two slits.
All right, tiny particles going through one slit or the other.
Right, that's what you'd think. But what happens is the electrons create an interference pattern on a screen behind the slits like they were waves.
Yeah, so they're going through both slits at the same time?
It's more like they're in this superposition going through both slits simultaneously. It's like they don't choose until they hit the screen.
Okay, this is definitely bending my brain.
Yeah.
But so this quantum world, it's got to be more than just electrons acting weird, right?
Oh, yeah. Quantum mechanics governs everything at the smallest level. Atoms, light, even black holes.
So it's super fundamental.
Absolutely. But it raises a big question. If everything's so uncertain at that level, how does anything work in a predictable way?
Yeah, that's what I'm wondering. Like, how do we have, solid objects and laws of nature if it's all fuzzy down there?
Well, the probabilistic nature of quantum mechanics, it doesn't mean the universe is random. It's more like the outcomes of individual events are uncertain, but overall behavior with lots of particles, that becomes predictable.
So it's like flipping a coin. One flip, you don't know. But flip it 1,000 times, you'll get close to 50 heads and tails.
Perfect analogy. And that's how we use quantum mechanics to make predictions. Even though the underlying world is probabilistic, the large-scale effects are consistent.
Okay, I'm starting to see how it all fits together, but how does quantum mechanics connect to the big picture stuff? Like the Big Bang, the possibility of other universes.
That's where it gets even more fascinating. One of the biggest challenges in physics is to unify general relativity, which describes gravity and the large-scale universe.
Right, Einstein stuff.
Exactly. Unify that with quantum mechanics. We need a theory of everything, something that bridges those two worlds.
A theory of everything. That's like the holy grail of physics, right?
It is, and it's something Hawking dedicated a lot of his work to. He explored ideas like string theory, which says the fundamental building blocks of the universe aren't particles, but tiny vibrating strings.
Tiny vibrating strings. Okay, we're officially in the realm of the mind-blowing.
It's a wild concept, for sure. And string theory is still very much a work in progress, but it offers this tantalizing possibility of unifying gravity and quantum mechanics.
And if we could do that, unify those theories, what would it tell us?
It could potentially unlock the secrets of the very early universe, like how the Big Bang happened, and maybe even shed light on the possibility of other universes.
Other universes.
Yeah.
Like a multiverse. Now that's some next level stuff.
It is, and it all ties back to one of the most fundamental questions. Why is our universe the way it is? Why do the laws of physics seem so perfectly tuned for life to exist?
Yeah, it's almost like the universe was made just for us.
That's the idea behind the anthropic principle, which says the universe must have these properties because, well, we're here to observe it.
So either we're incredibly lucky, or there's something more to it, some kind of grand design.
Hawking didn't believe in a personal God in the traditional sense, but he did believe that finding a complete theory of everything would allow us to know the mind of God in the sense of understanding the fundamental principles that govern the universe.
That's a really powerful idea, to think that through science, we could grasp those fundamental principles.
It is, and that's what makes Hawking's work so inspiring. He never stopped asking those big questions.
And he never lost that sense of wonder, that curiosity about the universe.
Exactly, and I think that's something we can all take away from his work, that drive to understand, to explore the mysteries of the cosmos.
It's been an amazing journey, exploring all these mind-bending concepts with you. Any final thoughts for our listeners as we wrap up this deep dive?
Just this. Keep looking up at the stars, keep asking those big questions, and never lose that sense of awe.
Beautifully said. And to everyone listening, thank you for joining us on this deep dive into the mind of Stephen Hawking. We hope it's inspired you to keep exploring the wonders of the universe. Until next time.